Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Hello everybody and welcome to this presentation. After discussion of membrane design and performance evaluation in 3 lectures, now one of the important fundamentals that have to be considered in the membrane design is energy and sustainability considerations. In this lecture, we go on the course with this topic as the last lecture of section 4. Energy and sustainability considerations in reverse osmosis. Reverse osmosis has the most significant impact on sustainability and energy consumption of any process in pressure-driven membranes. Reverse osmosis uses the most energy and often has the lowest water recovery and highest waste production of any common water treatment process. The feed pumps consume the most energy in a reverse osmosis plant. The feed pressure is dictated by the osmotic pressure at the concentrate end of the pressure vessels with enough additional pressure to overcome head loss and provide a driving force for mass transfer through the membranes. For example, for a brackish water system with 2000 mg per liter of TDS, the feed water osmotic pressure is about 1.7 bar. With 80% recovery and a concentration polarization factor of 1.1, the osmotic pressure at the membrane surface at the concentrate end of the pressure vessel is 9.4 bar. With additional pressure to overcome head loss and to provide a driving force, a feed pressure of at least 10 bar would be needed. In another example, a reverse osmosis system treating seawater with a TDS of 35,000 mg per liter at 50% recovery and concentration polarization factor of 1.1 has to overcome an osmotic pressure of about 56 bar. Some seawater reverse osmosis systems operate at feed pressures as high as 85 bar. The feed pumps on such a system would consume 5.6 kWh per cubic meter or 30 to 40 times the energy consumption of a conventional surface water filtration plant. It is important to realize that osmotic pressure is a fundamental thermodynamic limitation that cannot be overcome by advances in membrane technology. Better membranes can only improve separation, increase the rate of mass transfer, reduce the size of plants, and improve cost effectiveness, but cannot change the basic thermodynamics of osmotic pressure. Nevertheless, reverse osmosis systems can be designed to reduce energy consumption. 2 or more stages with booster pumps between stages allow for lower pressure feed pumps, so water in the first stage is produced at lower pressure and the pressure is increased in each subsequent stage as the osmotic pressure increases. The result is lower overall energy consumption. Energy recovery devices are also an important part of the design. Ultimately, however, the best way to reduce energy consumption from a reverse osmosis system is to select the water supply with the lowest possible TDS and therefore the lowest osmotic pressure, if multiple water supply are available. A second significant environmental concern for reverse osmosis facilities is the low product water recovery compared to other water treatment processes. For inland systems, low recovery has two negative consequences. As already discussed in the previous lecture, first, an inability to recover a high fraction of the feedwater is simply a poor use of scarce natural resources. Second, the unrecovered water becomes the concentrate stream that must be disposed of. The high salinity of the concentrate stream greatly limits the disposal options because of the potential for contaminating the scarce freshwater resources. Thus, increasing the recovery of product water and decreasing the volume of concentrate is an area of active research. For example, increasing recovery from inland brackish water reverse osmosis facilities involves preventing the precipitation of sparingly soluble salts. As noted earlier, SCADE inhibitors are used to prevent precipitation and increase recovery up to a point. However, SCADE inhibitors are limited in their effectiveness, and more aggressive strategies typically must be employed to achieve recovery of greater than 90%. Some strategies to increase the recovery have been mentioned in the previous lecture, but one strategy is also to provide an intermediate treatment process between two stages of reverse osmosis membranes. For example, since calcium is often the limiting cation, lime softening can be an effective intermediate strategy. Softening can also be effective at removing other SKS causing constituents, including barium, strontium, and silica. However, the high alkalinity and hardness present after a first stage of reverse osmosis can lead to high doses of lime or sodium hydroxide. Doses in excess of 1000 mg per liter have been reported in the experimental studies. Similarly, high doses of acid can be necessary to reduce the pH after softening. The high doses also lead to a large amount of lime sludge, another waste stream. Thus, the cost and waste production of interstage treatment must be balanced against the reduced waste production resulting from higher water recovery. Brine concentrators and crystallizers also additional technologies to reduce the volume of concentrate and can lead to zero liquid discharge in which the only residuals from the facility are solids. While brine concentrators and crystallizers are used in some industrial processes such as the power generation industry, they are expensive, energy intensive, and have not yet been used in the municipal water treatment industry. Energy and sustainability considerations in membrane filtration. Life cycle assessments have demonstrated that the environmental impacts of membrane filtration, like many other water treatment processes, are dominated by energy consumption during the operational phase of life. Thus, design decisions that affect energy consumption, largely through operating pressure, will tend to affect sustainability considerations. The study found that operation at low flux was more environmentally favorable. Low flux operation requires more membrane area to produce the same flow, so the main disadvantage is the large increase in equipment fabrication and plant concentration impacts and cost. Low flux operation allows the system to operate at lower pressure, reducing electrical energy consumption. Low flux will also decrease the frequency of backwash and cleaning, reducing environmental impacts associated with chemical production, transportation, and waste disposal. For five indicators such as global warming, human toxicity, freshwater aquatic toxicity, marine aquatic toxicity, and terrestrial toxicity potentials, the lowest evaluated flux, 10 liter per square meter in hour, was the most environmentally favorable operating condition. At any flux, energy consumption can be affected by system design. The pressure required to maintain constant flow through the membranes increases as the membrane falls. Increasing pressure requirements can be accommodated several ways. The pump system can be designed to operate continuously at the maximum pressure, and the excess pressure can be dissipated through an adjustable valve, or the pump can be equipped with a variable frequency drive or VFD. Operating the pump at maximum pressure wastes energy, and VFDs are the preferred method of flow and pressure control from an energy efficiency perspective. Many membrane manufacturers design their system with VFDs. Another design factor that will affect energy consumption is whether the system operates in a cross-flow or dead-end mode. Cross-flow filtration requires much larger feed pumps than dead-end because a substantial portion of the feed flow is recycled. The specific energy consumption associated with cross-flow pumping can be triple that of dead-end operation. One design decision that probably does not have much effect on sustainability is the specification of microfiltration or ultrafiltration filters. In full-scale operation, microfiltration and ultrafiltration systems tend to be designed for similar fluxes and operate at similar pressures, suggesting that the environmental impacts are also probably similar. Sustainability should be considered when comparing rapid granular filtration and membrane filtration as alternate filtration strategies. The situation is typically more complex because the selection of the filtration technology may influence the selection of other processes within the plant. For instance, in some cases, the use of membrane filtration may eliminate the need for coagulation, reducing the environmental impacts associated with chemical production, transportation, and sludge disposal. Granular filtration plants with significant protozoal removal requirements may need ozonation or UV disinfection facilities that would not be needed with membrane filtration. On the other hand, membrane filtration systems will use cleaning chemicals that are not used in rapid granular filters. In comparison with energy consumption, a membrane system that averages 0.6 bar feed pressure at 95% recovery and 80% pump efficiency would have a specific energy consumption of 0.022 kilowatt-hour per cubic meter compared to 0.01 to 0.014 kilowatt-hour per cubic meter for granular filtration. Residuals disposal. Some of the requirements which have to be considered in the residual disposal include least expensive, acceptable according to the local discharge regulations, and considering residuals from pre-treatment and from membrane treatment. Some of the options for reverse osmosis and nanofiltration concentrate disposal are as follows. Discharge to surface waters such as sea, rivers, lakes, or reservoirs. Injection well, that is a device that places fluid deep underground into porous rock formations such as sandstone or limestone or into the shallow soil layer. Evaporation ponds as a low-cost option for the areas that there is no limitation in land for construction of the ponds. Evaporators as an option for the areas with land limitation. Brine concentrators and crystallizers, as noted earlier, are additional technologies to reduce the volume of concentrate and can lead to zero liquid discharge, in which the only residuals from the facilities are solids. Wastewater collection system can be applied as an option if the centralized collection system is available. Zero liquid discharge is an engineering approach to water treatment where all water is recovered and contaminants are reduced to solid waste. While many water treatment processes attempt to maximize recovery of fresh water and minimize waste, zero liquid discharge is the most demanding target since the cost and challenges of recovery increase as the wastewater gets more concentrated. The cost and environmental impact of each option vary significantly based on many factors. Choosing management options for the concentrate disposal requires careful consideration of applicable discharge regulations, availability of disposal methods, and the economic feasibility of treatment. Now this lecture finished. In this section, you learn how to design a reverse osmosis system, how to evaluate a membrane performance, and some energy and sustainability consideration. Now you need to improve your knowledge with more exercises. Thank you for your attention.